Hello, today we'll be solving problem 3.22. So in problem 2.25 it's given to us that the potential on the axis of a uniformly charged disk is as is listed below, and on the axis, meaning that theta is 0. And so now we basically want to find it when theta is anything. So in part A we want to use this together with the fact that the Legendre polynomial of 1 equals 1 to evaluate the first three terms in the expansion of equation 3.72, which I have below, for the potential on the disk at points off the axis, assuming that r is greater than our radius. And in part B we'll do the same, but for r is less than our radius, using equation 3.66, which I also have below. So for part A, we can first just rewrite our potential now for r and when theta is 0 as the sum, this is from equation 3.72, from L equals 0 to infinity of BL over L, R to the L plus 1 times PL of 1, and this is becoming from, because cosine of 0 equals 1, so that's where we're evaluating it, and then we can say that is equal to then just the sum from 0 to infinity of BL over R to the L plus 1, and then that can be set equal to what was given to us, sigma over 2 epsilon naught times the square root of r squared plus big R squared minus r. And now, because we can say, since little r is less than our radius, we can say that the square root of r squared plus big R squared minus r, we can say that that is equal to, we'll factor out little r, and that will be 1 plus big R over little r squared, the square root of that, minus 1. So here we have little r factored out. And then the Taylor series expansion of the square root of 1 plus x is as followed here. So why don't we just say that x is basically big R over little r squared. So we can use that and say then that the square root of 1 plus big R over little r squared minus 1, we can rewrite that as 1 plus 1/2 big R squared over little r squared minus 1/8 of r to the 4 over little r to the 4, and then plus, just repeating, and then we'll do minus 1 for that last part here. So now we can then say that the sum from L equals 0 to infinity of b to the L over r to the L plus 1 is equal to, and we're just bringing this down, sigma over 2 epsilon naught times all of what we just found. And we'll put our r in front of there. 1 plus 1/2 r squared over r squared minus 1/8 big R to the 4 over little r to the 4 plus, repeating, minus 1. And then this will be equal to, well, let's simplify this a little. We can cancel those out, and then we can also factor out our little r. So we'll go like that. And so then that will just be equal to sigma over epsilon 2 times epsilon naught times big R squared over 2 little r minus big R to the 4 over 8 little r cubed plus, repeating, or continuing, not repeating. And so then, well, let's expand here now. we can say that b naught over little r plus b1 over r squared plus b2 over r cubed plus continuing is equal to sigma over 2 epsilon naught times r big R squared over 2r minus big R to the 4 over 8r cubed. Continuing. And so then, why don't we just compare powers of r? So we can do that by looking here, like this, right? So we can see then that, for example, B0, I said not earlier, but it's 0, B0 over R would have to be equal to sigma over 2 epsilon naught times R squared over 2R, because that's the only term that would get us what we need there. So then we can solve for that and say that B0 is going to be equal to sigma R squared over 4 epsilon naught. And we can do that for the rest. So we can then see that B1 has to be equal to 0 because we have no R squared, 1 over R squared term. And then B2 will be equal to, looking here, we can just say B2 will be equal to negative R big R to the 4 over 8 times our sigma over 2 epsilon naught. So that will get us negative sigma big R to the 4 over 16 epsilon naught. Okay, and so now using our equation 3.72, we can say that the potential of r theta is going to be equal to, we can factor out sigma r squared over 4 epsilon naught times 1 over r p0 of cos theta, so that's our Legendre polynomial, minus r squared over 4r cubed times p2 of cosine theta, and continuing. And so then that we can also just rewrite. We can say then that our potential for any r and theta is equal to, we can factor out our 1 over little r, sigma r squared over 4 little r epsilon naught times 1 minus, because p naught of cos theta is 1, right? Minus 1/8 times, go r over little r, this whole thing squared, times, now we're plugging in this, right? So it'll be 3 cos squared theta minus 1 plus, continuing. And then that is for when r is less than big R, our radius. So there is the answer to part A, excuse me. All right, now for part B, we're going to be using our second equation, 3.66. So I have that written here, and we have to break it up into two parts, the northern hemisphere and the southern hemisphere. So for the northern hemisphere, we'll be looking at when theta is greater than or equal to 0, and less than or equal to pi over 2. And for the southern, it will be pi over 2 is less than or equal to theta is less than or equal to pi. So looking at the northern, we're going to do that one first. We can, again, using the same strategy, we can say that the potential of R, and when theta is 0, going to be equal to the sum 0 to infinity, a L R to the L, and then our Legendre polynomial of 1. Now again, because cosine of 0 here is what we're plugging in, right, is equal to 1. So then again, we'll just rewrite it. The sum from L equals 0 to infinity, a L R to the L, and that has to be equal to then sigma over 2 epsilon naught times square root of r, little r squared, plus big R squared minus little r. And so now here instead we're saying that since little r is less than our radius, we will say that the square root of r squared plus big R squared is going to be equal to, now we'll factor out big R instead, right, because that's what we can do, times, so I'll have little r over big R squared minus plus 1, sorry. And now again, we're just going to use the same technique with taking the Taylor series expansion of 1 square root of 1 plus x, right here, right? And we're basically saying that now little r over big R squared, that's, we're plugging in for x. So then we can just say that this is equal to r times 1 plus 1/2 r over big R squared minus 1/8 little r over big R to the 4. Continuing. So then we can say that the sum from 0 to infinity of a L R to the L has to be equal to sigma over 2 epsilon naught times, and I just am now factoring r back in, r plus 1/2 r squared over big R minus 1/8 little r to the 4 over big R cubed. Continuing, and then we have to keep that minus r because that wasn't factored out or anything. So that's from up here. And then from there, we're just going to again compare our powers, right? So we want to say, right, when, for our first term, when r is 0, what gives us little r being 0? And when r is 1, what gives us little r being 1? And for 2, continuing. So we're just going to compare our powers. All right. So from that, we can just say that a0 is going to be equal to sigma over 2 epsilon naught big R, right? Because this here is the only term when little r is not there. And then same thing for a1 is going to be equal to negative sigma over 2 epsilon naught, because the only term with r to the 1 is right here, and that's just a negative of our coefficient in front. And then we can say that a2 is going to be equal to, whoops, don't know what happened, sigma over 4r epsilon naught, because now for this a2 we want here, right? Okay, and so then, again, using our equation right here, we can just say that v of r theta for any r and any theta is going to be equal to sigma times big R over, actually let's just write it like this first, sigma over 2 epsilon naught times big R, and then R to the 0. So I'm just writing this to be more explicit. Sorry. Our Legendre polynomial 0 of cos theta, now minus R to the 1 P1 of cos theta, and then plus 1/2 over R squared, little r squared, P2 of cos theta. And so now that can be written as, well, we'll factor out big R, and so we'll do that here now. So sigma times big R over 2 epsilon naught times 1, because R to the 0 is 1, P0 of cos theta is 1, so then minus, we can say R over R, because big R was factored out, times cos theta, because that's what our first term is, and then plus 1/4 times R over big R squared, and plugging in that Legendre polynomial times 3 minus cos of theta. Sorry, that was quite messy. Excuse me, I said the right thing, but wrote the wrong thing. 3 times cos of theta minus 1. And then that will be for when R is less than the radius in the northern hemisphere. Okay. Now we're going to need to do the same for the southern hemisphere. But for our southern hemisphere, we will just use, now we'll have to use the potential at R and pi, right? Because theta being 0 is not an option for that southern hemisphere. So we can plug that in, and so that's going to give us the sum from L equals 0 to infinity of a L R to the L, and now we'll have P L of -1, because cosine of pi is equal to -1, right? And so then that can be rewritten as the sum from L equals 0 to infinity of a L R to the L, and then we'll have just -1 to the L. And then that will have to be equal to our sigma over 2 epsilon naught times the square root of little r squared plus big R squared minus little r. And so now just comparing this to what we just solved, the only difference is that we have this -1, right? And so the only difference, I'll write that here, only difference between northern our northern AL coefficient and our southern is the sign. So therefore, well, I'll just highlight this real quick. So that's due to that. So for odd, only odd is going to be affected, right? Because -1 to any even is going to be equal to 1, right? So only our odd terms will be affected. So you can say A0 of south is just going to be the same as A0 of north. But A1 of south is going to be equal to negative times negative A1 of north. And same thing for the A2, it'll just be the same as A2 of the north. So we don't have to go through all the same steps that we did here. We can just compare those, and therefore we can just say that our potential is going to be, our potential at any r and any theta is going to be equal to sigma times big R over 2 epsilon naught times 1 plus little r over big R cos theta plus 1/4 little r over big R squared times 3 cos theta minus 1. Right, and that's again for r is less than our radius in the southern hemisphere. And so again, when we're comparing the solution to we got up here, the only difference is this sign right here. So that is our solution and solves part B.